guys, welcome to your last lesson in Unit 7. We're going to relate the idea of free energy and spontaneity to equilibrium and our equilibrium constant K. So we're kind of coming full circle here. Okay, so we know that if delta G is 0, we said this kind of briefly, then we are at equilibrium. Well, something else that tells us we're at equilibrium is whenever K equals 1. Way back when we talked about, remember the equilibrium constant is products over reactants. Okay, so if delta G is 0 and K equals 1, then we are at equilibrium. Delta G is less than 0, so delta G is negative and K is greater than 1. It means we're product favored. So that means we are spontaneous. And then if delta G is greater than 0, K is less than 1, that is non-spontaneous. So that's kind of how we combine these two concepts of Gibbs free energy and the equilibrium constant in order to see that both of us can indicate, or both of them can indicate to us if a reaction is thermodynamically favored or not. So let's kind of summarize what we know. If a reaction is thermodynamically favored, then it is considered spontaneous. The delta G value has to be negative. It's going to proceed in the forward direction because it's product favored and it's spontaneous. And we're going to have a large K value greater than 1. On the flip side, if something is not thermodynamically favored, we call it non-spontaneous. Its Gibbs free energy value is positive. So it's going to proceed in the reverse direction, and therefore it's reactant favored and it has a small K value. If we are at equilibrium, then of course delta G is 0 and K is equal to 1. So up until this point, we have been talking about calculating delta G when we're at standard conditions. But what if we're not at standard conditions? We have this equation below, delta G, which tells us that delta G not at standard condition is equal to the delta G at standard conditions plus R, which is the gas constant, T, temperature in Kelvin, times the natural log of Q. Remember, the reaction quotient is calculated just like K. So we have our products over reactants raised to their coefficients, okay? Now something I want to point out, this is an R value we don't use as often. All right, 8.314 joules. Now we're dealing with heat and energy here, so we need the R value that's in joules. So be careful when pulling it off of your reference table that you use the correct R value. Okay, so now if we were at standard state, then Q would be 1, because remember standard state is when everything's at 1 molar. So Q would equal 1, and if I plug a 1 in right here, I get delta G equals delta G naught because we are at standard state. Okay, so basically what this equation does is it corrects for not being at standard conditions. So let's look at this example. We are given delta G at standard conditions. That's given to us right here. But we're asked to determine delta G under the specified conditions. So delta G not at standard is equal to delta G at standard plus RT natural log of Q. All right, so delta G standard is 33.0 kilojoules per mole. That was given to me up above. Plus my R value is 8.314 joules per mole Kelvin. This is in kilojoules, so I need to convert it 0.0081314 times the temperature, which is 25 degrees Celsius, which is 298 Kelvin, times the natural log. Now I have to calculate Q. So in this case, it's going to be using pressures because that's what I'm given. Products over reactants. So the pressure of H2 which is 0.25 cubed times the pressure of N2, 0.87 divided by the pressure of NH3 squared. And when I do that math, I get 8.17 times 10 to the negative 5. All right, so now I'm going to multiply all of that and add it to 33, and I'm going to get that delta G is equal to 9.69 kilojoules per mole. All right, so let's look at this example. We're told to consider the ammonia synthesis. So that's the creation of ammonia. So we're not given the reaction, so we need to write it. So we have N2 plus 3 H2s yields 2 NH3. And if you're like, whoa, how did you know that? Okay, first of all, it's the synthesis of ammonia. So ammonia is what we're making. And then if you look down here, it's easy to see then that N2 and H2 are your reactants. And then you can just balance the equation. Okay? So we are asked to determine what delta G is because we're asked to predict the direction it's going to shift. And how does delta G tell us that? Well, remember, if we are at equilibrium, delta G would equal 0, okay? So if delta G is negative, the way that we need to increase it, so we would shift right. And if delta G is positive, we are going to shift left. So it's just kind of another way to look at which way we have to shift to get to equilibrium. Okay, so we're going to calculate delta G. We're given the standard, negative 33.3 kilojoules per mole, plus R is 0.08, or excuse me, 0.008314, because we have to convert it to kilojoules. It's given to us in joules per mole Kelvin. Our temperature is 25 degrees Celsius, which is 298 Kelvin. And then natural log of Q, well, we have to calculate Q given these pressures here. So my product, NH3, has a pressure of 1 squared over, we have N2, 1.47 times H2, 0.01 cubed. And when you do that math, you get 680,272. So now when I do that math, I actually get, crazy enough, 33.3, which means that we are at equilibrium. So in this case, we're already at equilibrium, so we don't have to shift. Now we're going to do the same thing, but this time all of our pressures are 1 atmosphere. And so when I plug in 1 for all of my pressures, whoops, to 98, I get a Q equal to 1. Well, we all know the natural log of 1 is 0, so we get that delta G is equal to negative 33.3, which means that we are going to have to shift right in order to reach equilibrium. All right, last but not least. So here's the equation we've been working with, calculating, left out the delta here, calculating delta G when we're not at standard conditions. But when we are at equilibrium, then we know that Q equals K, because we're at equilibrium, and delta G equals 0. So what if we plug these two things in? Delta G equals 0, and Q equals K. Then we get this equation right here, which is given on your reference sheet. So first thing, this top equation up here, it's not given on your reference sheet, but it's easy enough to find it by just adding. So we've got adding this over here, oops, plus RT natural log of K, and setting that equal to delta G. So it's very easy to get it from the equation that you are given. Okay, so anyways, we're given this on our reference sheet. What we can do with it is we can use K to calculate delta G, or we can use delta G to calculate the equilibrium constant. Okay, so let's look at an example. Given that the standard free energies of formation for each of the individual parts, calculate the solubility product constant K for AgCl. So in order to do that, we've got to calculate delta G first. So my reaction is solid AgCl dissolving into aqueous silver and aqueous chlorine. So to find delta G for the reaction, given the standard values, we do products minus reactants. So we've got 77.1 plus chlorine is negative 131.2 minus my reactant, which is negative 109.8. All of these are in kilojoules per mole. So when I do that math, I get that delta G is equal to 55.7 kilojoules per mole. So now I can use that value and plug it into K equals negative delta G over, goodness gracious. Let me try this again. I realize I didn't show you last slide. So you're given this equation on your equation sheet. And I said that allows us to use K to calculate delta G or to use delta G to calculate K. We didn't really look at how we solve for K because it's not given in that form on the equation sheet, right? So we're going to divide both sides by negative RT. And then that gets rid of negative RT. And then what is the opposite of the natural log? We raise everything e to it. So K equals the natural log e raised to the negative delta G over RT. So that's how we calculate K using the equilibrium, using the free energy. So E raised to the negative 55.7 divided by, remember this is in kilojoules, so we got to put R in kilojoules, 0.008314 times the temperature, which is 298. So then when we do that math, we have E raised to the negative 22.5. And that gives me 1.7 7 times 10 to the negative 14. Or excuse me, to the negative 10. Gracious. All right. So let's think about this for a second. My delta G was positive, so that means it's non-spontaneous, which should mean I have a K that's much less than 1, which I do here. All right, so I'm given another one, the overall reaction from the rusting of iron, and we're asked to calculate the equilibrium constant. So here we truly are putting everything together, because in order to get the equilibrium constant, we need delta G. And in order to get delta G, we're going to have to calculate delta H and delta S. So let's do this one at a time. I'm going to start with delta H. Products minus reactants. So 2 times negative 826 minus, both of my reactants are 0. So I get negative 1652 kilojoules per mole. Got to pay attention to our units. Delta S, also products minus reactants, so 2 times 90 minus 4 times 27 plus 3 times 205 equals negative 543 joules per mole. Now that we have both those, we can calculate delta G. So my delta H value is negative 1652. My temperature is at standard, so 298. And then my change in entropy was in joules, so I've got to change that to kilojoules, negative 0.543. And when I do that math, I get negative 1490.2 kilojoules per mole. So that's my delta G value. So now I've got to calculate K from delta G. So I have negative delta G, e to the negative delta G over RT, e to the negative 1490.2 kilojoules divided by 0.008314 times the temperature, which gives me e raised to the 601, which is actually too large for our calculator, so we are just going to leave it as e to the 601. All right, so that is an extremely large number, which being greater than 1 goes along with delta G being negative, which all goes towards a spontaneous reaction. All right, guys, that is it for thermochemistry.